Hi everyone, greetings of the day. I am Dr. B. Ravi Chandra, Associate Professor in the Department of ECE. Today I am here to discuss about another technique which is nothing but Chebyshev filter. In the last session we have discussed about the technique which is nothing but Butterworth filter. Once again we will recall the thing why we are using these particular techniques. Here we are discussing about two filters. One is nothing but FIR filter, which we have already discussed in the last sessions, and another filters which is nothing but IIR filter. So the difference between these both FIR and IIR filter is the main difference. Here both are used to convert the analog filters into digital filters. But what happens here, in the FIR filter we can directly convert the analog filters into digital filters. But coming to these IIR filters, what happens here, it is not directly converted from analog to digital. First, what we need to do, we have to design the analog filters. That means we have to design the transfer function of the analog filters. After designing the transfer function of the analog filters, then we need to convert that transfer function of the analog filter into digital filter. This is the step which we use in this particular IIR filter. So for that purpose, first what we are using two filters, which is nothing but Butterworth filter and Chebyshev filter. In the last session, we discussed the Butterworth filter, how the analog filters is going to design. That means how the transfer function of analog filter is designed by using the Butterworth filter. And also we have taken two problems and we have discussed the thing how the conversion is going to happen. The same thing, the another technique which is used to design the transfer function of the analog filter is nothing but the Chebyshev filter. So this is one of the another technique which is used to design the transfer function of the analog filter. Let's see what are the contents we are going to discuss in this particular session. So why we are using Chebyshev instead of Butterworth? Already we discussed Butterworth. Then why we are going with the Chebyshev? We'll discuss that thing, and later introduction to the Chebyshev filter, and the same thing, how the design of analog low pass filter will take place and what are the steps that involves in the designing of the analog low pass Chebyshev filter, and finally just we will see how the steps is going to design by taking two problems. So these are some of the contents which is going to discuss in this present session. So first of all, we will recall the thing why we are going with the Chebyshev filter instead of Butterworth. Though we have Butterworth filter already, why we are going with the Chebyshev filter? These are some of the drawbacks that overcomes by the Chebyshev filter to the Butterworth filter. The first one, what is saying, the Butterworth filter changes slowly. It changes slowly from passband to stop band. So this is the first thing. The Butterworth filter changes slowly from passband to stop band, which means it doesn't block the unwanted signal. This is one of the drawback. That means it will change from passband to stop band. But what happens here? It does not blocks the unwanted signals. But coming to the Chebyshev, though it also changes from passband to stop band. But what happens here? It blocks the unwanted signals. This is one of the main difference that are one of the main drawbacks that is present in the Butterworth, which it will be overcome by the Chebyshev filter. The another thing, the Butterworth filter sharpers needed to use more components. So here the complexity is one of the point that comes into Butterworth filter. Why? Because it used more components while designing the Butterworth filter. But coming to the Chebyshev filter, the fewer components will be used here, so and it is very cheaper to build. So this is another drawback that is present in the Butterworth filter, which were overcome by the Chebyshev filter. Now the third one, it's not very good when you need to clearly separate wanted and unwanted signals. Our agenda is to separate the unwanted signals from the wanted signal. That means we need to clear or we need to remove the unwanted signals from the original signal. But what happens here, it is not that much very good by the Butterworth filter to do this kind of thing, where Chebyshev filter will clearly sharp that particular signal by removing the unwanted signal with the original signal. And fourth one, the transition from passing to blocking signals is slow. It doesn't give precise result in some applications, not efficient. Coming to the Chebyshev, it is somewhat very efficient and accurate. We will get the accurate output. Finally, because it needs a higher order, the order that is, we know the values what we are taking, that capital N is equal to. So what happens here? It needs higher order to work well. It takes more time to calculate or process. Lengthy process will happen in this particular Butterworth filter. But what happens here? Though it takes the higher ordered filter and also usually uses the lower order filters, it is somewhat very fast in calculating the particular designing of the analog filter. So these are some of the drawbacks that is present in the Butterworth filter, where how that drawbacks can be overcome by the Chebyshev filter. So based on this particular advantages which is present in the Chebyshev filter, let me see what are some of the introduction related to that particular Chebyshev filter. So already we have discussed same, just we will recall the thing. What is the purpose? Why the purpose of using this particular Chebyshev filter means just to separate one group of frequencies from another. Similar, what means it is nothing but just we want to separate the unwanted things from the original signal. That's why unwanted things is nothing but unwanted frequencies. So from the original signal, we are removing or we are separating that one group of frequencies, which is nothing but the unwanted signals with the original signals, like passing useful signals and blocking the noise. So this is one of the purpose why we are using the Chebyshev filter. And based on this particular advantage, this is one of the good advantages that is present in the Chebyshev filter, that is speed. Much faster than the filters like window sink filters or else Butterworth filters. Why? Because they are using the recursion method. Because of this particular method used by the Chebyshev filter, it will be in a fast, that means speed. So a step-by-step repeated process will be taken place. Instead of convolution, this uses the recursion method. Convolution, as usual we have studied in the previous lectures, how the convolution, what is meant by convolution, and we have seen the problems related to the convolution where we came across the lengthy process that happens in the convolution. So that if to solve that particular convolutions, what happens here, it takes much more time. So for that, instead of the convolution, the Chebyshev filter uses the recursive method. Because of using this particular recursion method, this will be much faster than the other filters. So how they work? So these will be work mostly by designing the method with Z transforms. Because of this particular method which uses, that is Z transforms, what we are using, because of these Z transforms, these are mathematical tools in digital signal processing, and these works depends upon the Z transforms. These filters allow ripples, that means small bumps in the frequencies response to get a sharper cutoffs. We will see this point related to this point. We will see with the help of the graphs in the next upcoming slides. So this ripple is a trade-off. More ripple is equal to better sharps. More ripple, better sharpness of the signal. So these are some more small introduction related to the Chebyshev filter. Depending upon this particular introduction, let me see the types of Chebyshev filters. We have two types of Chebyshev filters, that is type 1 Chebyshev filter and type 2 Chebyshev filter. So here, what will happen in this type 1 Chebyshev? What are they in this type 1 Chebyshev filter? So these are all poles filter. Only poles will be fine in this particular type 1 Chebyshev filter. In the pass band, they show equiripple behavior. Please keep it in mind. I will show that in the graph. In the pass band region, they show equiripple behavior. In the stop band, they show monotonic response. Just keep these two terms in mind. What happens in the pass band? They shows the equiripple. That means it will be in the form of equiripples in the pass band. Whereas coming to the stop band region, it will shows the monotonical response. That is no ripples. The response will be flat. So the ripple is controlled by a parameter with a parameter called as epsilon. Okay. So we'll see this in the form of a graph. See here, we got a graph which is between magnitude and frequency, and it's just see here red line. What is this red line? I told you that Chebyshev filter magnitude response. This ripple is nothing but magnitude response which is present in the pass band. See here, red line indicates Chebyshev filter magnitude response, and we told that it will be in the form of ripples in the pass band. Fine. Now, blue dashed line, maximum magnitude. So this is the maximum. What is the maximum magnitude response of the Chebyshev filter is 1. Okay. Now, green line, 1 by square root of 1 plus epsilon square. Second line, this line represents the ripple level in the pass band. What is the ripple level in the pass band? Just here, the ripple level in the pass band, which will be indicated by this green line, which is nothing but 1 by square root of 1 plus epsilon square. Now, purple line. See here, this purple line, which is nothing but 1 by square root of 1 plus lambda square, which is in the stop band. Okay, which is the level in the stop band. And orange line here, just observe in the x-axis, the orange line, which is omega p, that is cutoff passband edges. Cutoff passband edges, and finally the brown line, which is omega s, that shows the stop band begin. So from here the stop band begins. So in the previous we have seen 2 points. In the passband they show equiripples. See here, this total, which is nothing but the passband, and in the stop band it shows the monotonic response. See here, coming to the stop band, this all response is very monotonic, which they don't have any ripples. So this is one of the magnitude response, that means characteristics of the magnitude response of type 1 Chebyshev filter. Similarly, we will see the type 2 Chebyshev filter, where just is quite opposite. This filter contains both zeros and poles, where in type 1 it will have only poles in type 1, but coming to this type 2 Chebyshev filter, it will have both zeros and ones. And see here, in the stop band how it happens, it shows the equiripple behavior, where in the type 1 Chebyshev it is monotonic behavior, and in the pass band you can see the response is monotonic, where in the type 1 Chebyshev it is equiripple behavior, just a opposite, quite opposite of the type 1, which is nothing but type 2. So here the main difference from Butterworth, when we compare this Chebyshev with the Butterworth, all the poles of Butterworth lies in the circle. Okay, this is the one of the main point. When we compare this Chebyshev filter with the Butterworth filter, all the poles will lie within the circle. If we draw this, all the poles will lie within the circle, whereas Chebyshev filter poles lies on an ellipse in the complex plane. So it will lies in the ellipse in the complex plane. So these are the main 2 differences that is from Butterworth filter. So if you see the magnitude response of the type 2 Chebyshev filter or frequency response, see here, where the red line shows the passband filter response, magnitude response, and I told you that in the passband it is monotonic response. See here, there is no ripple. Fine. The flat passband up to omega p, it is flat passband. There is no equiripples. That is the orange color, which indicates the omega p, cutoff frequency, passband cutoff frequency. Now ripples in the stop band, you can see here, after passing through the omega p, the ripples has been started. Okay, you can see the ripples that is present in which region? Stop band region. You can see you can compare this particular graph with the type 1 Chebyshev filter, where the ripple is present in the passband and monotonic response present in the stop band. But here in type 2 it is quite opposite. Okay. Now horizontal lines represents what is the magnitude of this particular type 2 Chebyshev is blue line, which is 1, and the green line represents the 1 by square root of 1 plus epsilon square, and purple color represents 1 by square root of 1 plus lambda square. So this is the second type 2 Chebyshev filter frequency response, where depending upon these 2 characteristics of type 1 and type 2, let me discuss the steps to design, how the design will happen for creating the value transfer function of the analog low pass Chebyshev filter. It is somewhat similar when we compare it with the Butterworth filter, but small differences. Let me know that what happens in this particular design. So same, first step. In the first step, what we are from the specification given in the problems, with the help of that specification, first we are going to find out the order of the filter. We are going to find out the order of the filter. So what is the formula we are going to use for this is n greater than or equal to cos h inverse square root of 10 to the power of 0.1 alpha s minus 1 by 10 to the power of 0.1 alpha p minus 1 whole divided by cos h inverse of omega s by omega p. This is one formula. When we want to use this particular, when the specifications are given, that is omega s, omega p, alpha s and alpha p, which if these specifications are given in the problem, then we can use this particular formula. Otherwise, if only the specification which comes in the form of lambda and epsilon, so we can use this particular formula. 2 formulas depending upon the specification, we can use either this formula or else this formula. So by using this particular step, in step 1 we are going to find out the value of order of the particular Chebyshev filter. So we know that alpha p is nothing but the passband attenuation, alpha s is nothing but the stop band attenuation, alpha p is nothing but the passband edge frequency, omega s is nothing but the stop band edge frequency, and lambda is equal to square root of 10 to the power of 0.1 alpha s minus 1. So these are all the specifications, and in the first step we are going to find out the value of lambda, find out the order of the filter capital N. Now second, same. So this is the alternate formula. If the specifications on the linear scale, we can use this kind of this formula also. Let me see, depending upon the two formulas, I have taken two problems and we can discuss that how it is going to design. Now in the second step, what we are going to do, whatever the value which is formed in the step 1, if it is n greater than or equal to 1.7, if I get the value of order n is equal to or greater than or equal to 1.7, in the second step, what I am doing, I am round offing that particular calculated value capital, that is to the next higher integers. So I can write this n is equal to 2. 1.7 to the next highest integer, I am round offing that value so that I can get that capital N is equal to 2. So in the second step, I got the pure value capital N is equal to 2. In the third step, here we are going to find out the values of major and minor axis. Cap A and B, which are nothing but the values of A and B, which are nothing but the minor and major axis, and the formula is cap A is equal to omega p into mu to the power of 1 by n minus mu to the power of minus 1 by n by 2, and the formula which is the minor axis or major axis B is equal to omega p into mu to the power of 1 by n plus mu to the power of minus 1 by n by 2. So by using this particular two formulas, we can find out or we can calculate the values of A and B. Fine. So what is mu? Mu is nothing but epsilon to the power of minus 1 plus square root of epsilon to the power of minus 2 plus 1, and epsilon, what is the value of epsilon? What is the formula? Square root of 10 to the power of 0.1 alpha p minus 1. So based on these particular formulas, in the third step, we are going to calculate the value of major and minor axis, that is A and B. Fine. Now coming to the fourth step. So after getting that major and minor axis, so after calculating the values of A and B here, in this fourth step, we are going to calculate the poles of the Chebyshev filter, that is S. We are going to calculate the poles of the Chebyshev filter which lies on the ellipse using the formula. What is the formula I am going to use here? Sk is equal to A into cos phi k plus jb into sin phi k. Okay. So this is the formula which is used to calculate the poles of the Chebyshev filter. How many poles I need to calculate means it depends upon the value what we got in the step 2. So we got, for example, I told you that if I round off the value in the second step, I got n is equal to 2. So how many poles I want to calculate here? I want to calculate pole S1 and S2. See here, for k is equal to 1, 2, so on n. So I got the value here n is equal to 2. So how many poles I need to find out here? 2 poles, that is S1 and S2. Okay. So before that, we need to find out the value of phi k. So the formula for the phi k is equal to pi by 2 plus 2k minus 1 whole divided by 2n into pi. So with the help of this fourth step, we are able to calculate the 2 poles, that means the poles, by using the formula Sk. In the fifth step, find the denominator polynomial of the transfer function. Here, to find out the denominator of the polynomials, we need to find out the transfer function by using the above poles. So here I got 2 poles. So how I need to find out the denominator? So S minus S1, S minus S2, that means how many poles we are finding in the step 4, that many products we need to take here. So for example, here I got 2 poles. So I can form the denominator as S minus S1 into S minus S2. If I get here 3 poles, S minus S1 into S minus S2 into S minus S3. So depending upon the poles that we calculated in the fourth step, that many denominator polynomials we can find in the fifth step. And finally, in the sixth step, this is the main thing you need to keep it in mind very carefully. Here, to find out the value of numerator. So according to the value what we got, that is n. So here we got n is equal to 2 na, so it is even. So if I get n is equal to odd values, for x is equal to 1, 3, 5 and so on, what we have to do? We need to substitute s is equal to 0 in the denominator. Please keep it in mind, be careful. If n is equal to odd value, we have to substitute the value of s is equal to 0 where in the denominator polynomial and the find value. So here, whatever the value I get here, it will be equal to the numerator of the transfer functions. Don't be confused. We will see with the help of one problem. So just keep it in mind. What we need to do in the sixth step, we need to observe whether the value of n is odd or even. If the value of n is odd, what we need to do? We have to substitute s is equal to 0 in the denominator part, where the value which is formed, it will be equal to the numerator of the transfer function. If it is even, it says same, we need to substitute s is equal to 0 in the denominator polynomial. So after getting the result, what we have to do? We need to divide the result with the square root of 1 plus epsilon square. Small difference. Here, just we are going to substitute s is equal to 0 when n is odd. But when n is even, we are substituting s is equal to 0, and after getting that value, that result will be divided with the square root of 1 plus epsilon square. So after that, the value what I am going to get will be equal to the numerator of the transfer function. So these are the two conditions depending upon the value of n, whether it is odd or even. And finally, so these are all the six steps that involves to design the analog low pass Chebyshev filter. Just I have taken one problem. See here, given the specifications, I told you, depending upon the specification here, what they have given: alpha p, alpha s, fp, fs. So 4 specifications they have given, and asked to determine the order of the filter using Chebyshev approximation. He is asking to find out the transfer function of the analog low pass Chebyshev filter. Fine. So what are the specification we got here? Alpha p is equal to 3 decibels given, alpha s, fp 1 kilohertz, fs. So here we need to convert. Why? Because there he had given in the form of fp and fs, but we want the specification in the form of angular frequencies, omega p and omega s. What are the steps we have discussed in the previous slides? We have seen only omega p and omega s in the form of omega p and omega s, but here in the question they have given it is in the form of passband frequency and stop band frequency. So for that, what we are going to do? We are converting that particular frequencies into angular frequencies. For that, what is the formula? We know that it is a regular formula. Omega p is equal to 2 pi fp. So already we got fp. So if I calculate, it is 2000 pi radians per second, where the value omega p, and omega s is equal to 2 pi fs, and the value what I am going to get is 4000 pi radians per second. So here we got the perfect specifications: alpha p, alpha s, omega p and omega s. So with the help of these 4 specifications, let me start step by step what we have studied in the previous slide. In the first step, what we have to find out? We need to find out the order of the filter, capital N, and what are the specifications we got? We got alpha s, alpha p, omega p and omega s. So depending upon this specification, which formula I am considering? I am considering the first formula. We have seen 2 formulas in the step. So according to the specification what we got in the formula in the problem, so depending upon that specifications, I choose this particular formula. So what is that formula? N greater than or equal to cos h inverse square root of 10 to the power of 0.1 alpha s minus 1 divided by 10 to the power of 0.1 alpha p minus 1 whole divided by cos h inverse omega s by omega p. So after substituting all the specification, what the value I got here? 1.91. So what is the value of n I got here? N is nothing but greater than or equal to 1.91. Fine. So in the second step, we just round off that particular n value into the next higher integer. So the next higher integer of n is equal to 1.92 will be equal to 2. So in the second step, I rounded the value to the next higher integer and I got n is equal to 2. So here, what here? The n value is in the form of even, and the oscillatory curve starts from where it is going to start. Just we have seen the frequency responses in the previous slides, type 1 and type 2. So if the value of n is even, the oscillatory curve, the curve will start from 1 by square root of 1 plus epsilon square. Okay. So if it is odd, it will start from 1 by square root of 1 plus lambda square. So depending upon the value of n, where the oscillatory curve starts, it will show. Fine. So we got 2 steps. In the third step, we need to calculate the major and minor axis, that is A and B. So first to calculate the values of A and B. Why? Because we know that A is equal to, so this is the main formula, A is equal to omega p into mu to the power of 1 by capital N minus mu to the power of minus 1 by capital N. Here we don't know the value of mu. Okay. So to find out the value of mu, just recall the formula. What is the value of mu here? Formula, mu is equal to epsilon to the power of minus 1 plus square root of epsilon to the power of minus 2 plus 1. So to find out this mu value, this is the formula we need to use. So here we don't know the value of epsilon. So further, just again go back to the formula. Epsilon is equal to square root of 10 to the power of 0.1 alpha p minus 1. So by substituting the alpha p, what is the value I got here? Epsilon. Epsilon is equal to 1. So with the help of this value epsilon, then we can compute mu is equal to, substituting epsilon is equal to 1. I got the value of mu is equal to 2.414. So after getting this value, now it is very easy to compute the values of A and B. So A is equal to omega p into mu value I got already 2.414 whole to the power of 1 by n. What is the value of n here? We got in the second step 2 minus mu to the power of minus 1 by n by 2. By substituting all the values, I got 9, 10 pi. What is the value? It is a minor axis capital small a, and similarly by computing the value capital small b is equal to same omega p into mu to the power of 1 by n plus mu to the power of minus 1 by n by 2. Small difference between a and b, just notation minus minus in a, and to calculate b it will be a plus, just small difference in the formulas. So after calculating the value, what I got here, b is equal to 2197 pi. So fine, here in the step 3 we calculated both the minor and major axis. In the step 4 we need to find out the values of poles. So how many poles we have to find out here? Why? Because we got capital N is equal to 2 in step 2. So now how many poles I need to find out? I need to find out 2 poles. So what is the formula we studied? Sk is equal to A into cos phi k plus JB into sin phi k, where k is equal to 1, 2, so on, capital N. So what is the value of capital N? So k is equal to 1, 2. How many poles I need to find out here? 2 poles. That is S1 is equal to S2 is equal to. Okay, 2 poles I need to find out. So before finding that value of S1 and S2, let's just first of all we find the value phi k is equal to pi by 2 plus 2k minus 1 by 2n. So here the value of k is equal to 1, n. So 5 values I need to find out. Why? Because phi 1 and phi 2. So to find out the value of phi 1, just substituting k is equal to 1, I got 135 degrees for phi 1, and phi 2, substituting k is equal to 2 here, I got the value is 225 degrees. So after getting the value of phi 1 and phi 2, similarly I am going to find out the 2 poles S1 and S2. So S1 is equal to, see here, S1 is equal to A into cos phi 1 plus J B into sin phi 2. And similarly for S2 is equal to A into cos phi 2 plus J B into sin phi 2. Sorry, here phi 1. So with the help of this particular formula and substituting all the value of phi 1 and phi 2, A and B values in the third step, we get S1 is equal to this and S2 is equal to these equations. So 2 equations I got, that is S1 and S2. Now in the fifth step, just we need to find out the denominator polynomials. So how many poles we got there? 2 poles. For that, just we can write d of s is equal to 2 poles now. That's why I am writing s minus s1 into s minus s2. Just by substituting this s1 and s2, which is formed in the fourth step, and multiplying this is the finalized equation what I got here. That is denominator polynomial I got. The denominator polynomial d of s is equal to s plus 643.46 pi whole square plus 1554 pi whole square. So this is the denominator polynomial. So finally in the sixth step, depending upon the value n. So what is the value I got here? N is equal to 2. So if the value of n is even, so what is the thing we need to do? First we have to substitute s is equal to 0. Okay, see here, first we need to substitute the value of s is equal to 0. So I am substituting, where I need to substitute that? In the equation what I got in step 5, d of s. So substituting s is equal to 0 in d of s, see here, I got this one, I substituted s is equal to 0. So only the terms what I got remain there is 643.46 pi whole square plus 1554 pi whole square. So after getting this particular thing, the result what I got here will be divided by square root of 1 plus epsilon square. See here, After substituting S is equal to 0, this is the result I got. So after getting that, the result what I got should be divided by square root of 1 plus epsilon square. So this is the final term. After calculating, 1414.3 pi whole square is the equation, which is the numerator part. So in the sixth step, we find the numerator part. So finally, after getting the denominator part in step 5, in the step 5 we find the value of denominator, and then the step 6 we find the value numerator. So after getting both numerator and denominator, finally the transfer function h of s is equal to numerator, that is step 6 divided by step 5. So numerator what I got here, 141.38 pi whole square, and the denominator what I got here, after multiplying this, it is in the form of a plus b whole square plus 1554 pi whole square. By calculating this particular thing, I am going to get s square plus 1287 pi s plus 1682 whole square pi square. So by taking the ratio of step 5 and step 6, we are going to find out the transfer function of the analog filter, that is analog Chebyshev filter. So this is the problem, how we are going to design the analog low pass Chebyshev filter. So this is the thing with one kind of specification, and we will take another problem which is specifications in another form. Just see here, obtain an analog Chebyshev filter transfer function that satisfies the constraints. What are the constraints? See here, 1 by square root 2 less than or equal to h j omega less than or equal to 1 for 0 less than or equal to omega less than or equal to 2, and another specification mod h of j omega less than or equal to 0.1 for omega greater than or equal to 2. So these are the constraints given. So with the help of these constraints or specifications, just we have to design the analog Chebyshev filter transfer function. So what are the values? Just we will see here. So see here, n greater than or equal to cos h inverse, we got the value lambda, that is 1 by square root, and epsilon, that is 1 lambda epsilon, and if you see here 4 by 2, so 4 is nothing but omega s, this is omega s, and this is omega p. So like this we got the specifications. So cos h lambda by 2 divided by, and depending upon the specifications we given, I have choose the second formula, okay, that is n greater than or equal to cos h inverse lambda by epsilon by divided by cos h inverse omega s by omega p. By substituting the values with the given constraints, so after calculating all the things, the value what I am going to get here, capital N is equal to 2.26. Now see here, in the second step, we need to round off this particular value to the next higher integer. So n is equal to 2.2 means I am round offing that particular value, capital N is equal to 3. In the second step, I found that capital N is equal to 3. Now see here, in the previous it is n is even, so that oscillator starts from 1 by square root of 1 plus lambda square. But see here, it is odd now. So where the oscillatory curve starts from? It starts from unity. Okay, from 1 it will start. The curve starts from 1. Now in the third step, same. We need to find out the value of major and minor axis A comma B. To find out the particular values, just first of all we write the formula of the A value and B value. See here, omega p into mu to the power of 1 by n minus mu to the power of minus 1 by n by 2. Here first we don't know the value of mu. So to find out the value of mu, just we are taking the formula. Mu is equal to epsilon to the power of minus 1 plus square root of epsilon to the power of minus 2 plus 1. So here, do you know the value of epsilon? No, we don't know the value of epsilon. Actually, we have given that epsilon is equal to 1. Right here, sorry. We know it is given in the constraints, epsilon is equal to 1. Directly we can take that epsilon is equal to 1. Otherwise, we have a formula to find out the value of epsilon. So by knowing the value of epsilon, just we can calculate the mu value and we get 2.414. So by calculating the mu, by substituting the value of epsilon is equal to 1, we will get the value 2.414. After knowing the value of mu, we can find out the value of A and B, that is minor axis and major axis. What is the minor axis value we got here? 0.596, and the major axis B we get here 2.087. So we calculated the major and minor axis in the third step. In the fourth step, we are going to get the poles. How many poles we want to find out here? depending upon the value of n is equal to 3, we have to find out the values. How many poles? 3 poles, that is S1, S2 and S3. So see, this is the formula. We know that Sk is equal to A into cos phi k plus JB into sin phi k, and k is equal to 1 to so on capital N, and we know the value of capital N. So how many? K is equal to 1, 2, 3. So before finding the value of poles, just we need to find out the value of phi k. So how many phi k we need to find out? That is 3. That is phi 1, phi 2 and phi 3. So we got the values 120 degrees, 180 degrees, 240 degrees. Now by using that particular values phi 1, phi 2 and phi 3, S1 value is equal to minus 3.3 plus J 18.23, and S2 is equal to, substituting all the values, we will get minus 6.6, and S3 is equal to minus 3.3 minus J 0.8.23. So we got 3 poles, that is S1, S2 and S3. In the fifth step, just we need to find out the, in step 5, just we need to find out the value of D of S, that is equal to S minus S1 into S minus S2 into S minus S3. Why? Because we have calculated 3 poles, S1, S2, S3. So depending upon the 3 poles, just we need to find out the denominator part. D of S is equal to S minus S1 into S minus S2 into S minus S3. So what I am going to get here, the denominator part, it will be like S plus 6.6 whole square plus 6.6S plus 343.2. So this is the value I am going to get in the step 5. And finally, in the step 6, just we need to find out the numerator of the transfer function, where in step 5 we will find out the denominator part, but in the step 6 we are going to find out the value of numerator part transfer function. So for that, just first we need to observe what is the value of n. N we got n is equal to 3, so which is odd. So if it is odd, just we need to substitute S is equal to 0 in the denominator part. So by substituting S is equal to 0 in the denominator part, what is the denominator part I got here? So this one, S plus 6.6 whole square plus 6.6S plus 343.2 we got. So by substituting S is equal to 0 here, here and here, only I get the value n of S, that is D of S, when S tends to 0, the value will be 2265.23. So what is this value? It is the value, numerator value. Okay, so it is the numerator of the transfer function I got in the step 6, because n is equal to odd. If it is n is equal to even, if I get the value numerator, then it will be divided by square root of 1 plus lambda square. But n is equal to odd now, just we are substituting S is equal to 0, so that I am going to get this value. So after getting the value, numerator part, finally we are going to find the transfer function of the analog Chebyshev filter, that is numerator divided by, that is step 6 here ma. So step 6 value divided by step 5 value. So here numerator divided by denominator part. So 2265.27, which is the numerator part, divided by the denominator, that is S plus 6.6 whole square plus 6.6S plus 343.2. Like this, we are going to find out the transfer function of the analog Chebyshev filter by using the 2 techniques. One is Butterworth and Chebyshev filter. Now, it is the thing is not completely completed. Why? Because first what we have done here, just we have found the value of the transfer function of the analog filter. Next we have another thing, that means the value which we find here, that is H of S, which is nothing but the transfer function of the analog, both Chebyshev or Butterworth. Just we got the analog filter, but now here we need to convert this particular analog filter into the digital filter. For these things, in the next upcoming classes, we will study about the linear invariant method and bilinear transformation method, which that 2 techniques are helpful to convert the transfer function which is formed by the Chebyshev and Butterworth filter into the digital filter. So that 2 techniques, linear invariant method and bilinear transformation method, will be discussed in the upcoming classes. Okay.